Hi, this is the topic 4.3 ions. And so today we're going to dive into charge of the atom and how atoms are not always necessarily neutral. At this point, we've kept everything as being neutral. That has been a lie. And so, like I said, we're going to explain how and why those charges form. As a refresher, remember of the three subatomic particles, the only one truly responsible for identifying the identity of the element is the proton. Neutrons and electrons have nothing to do with the identity of the element, and those two subatomic particles can vary in the atom. So neutrons' prime role in the nucleus is to help maintain stability of the atom. That decides if something is going to be radioactive or not. Electrons in the electron cloud decides if an atom is neutral, and that is because protons are equal to electrons. That's where we get that neutral side of things. Or it can form a charged particle or a charged atom called an ion. So again, thinking about charges, what two particles are responsible for the charge in the atom? So again, of the three, one of them is the proton, and that's our positively charged subatomic particle. And then we have the electron, which is our negative charge. Okay. So this is kind of to represent an atom and just kind of talk about net charge. So net charge just means total. If any of you have a job and if you look at your pay stubs, it talks about net pay or net gross income. And that's just how much money have you made for that year. So looking at the overall charge, we can say that we have 3 protons and 4 electrons. We have 1 more electron than protons. Therefore, this net charge is going to be a -1. In this example, we can see that they are clearly equal to each other. So this is what we've been using all along, is representing a neutral atom. Here we have more protons than we do electrons. We have 1 more proton than electron, so the net charge will be +1. So an ion, those two up above on the left and the right represent maybe an atom that's an ion, and that it's basically an atom that now has a charge, because again we can see that it has something to do with those proton-electron ratio. And so there's 2 options. You can either be a positive charge or negative charge. So how do we define those and why do they become what they become? It's because of electrons. And so cations are an atom that has taken on a positive charge. And in order for that positive charge to form, there had to be a loss of electrons. If you think about it, protons are positive, electrons are negative. You need more positives than you do electrons to have a net charge to be positive. Therefore, electrons had to be lost. On the flip side of things, we have an anion. Anions are the negatively charged ion form. And again, thinking of it as a ratio, in order to take on a negative charge, you therefore have to have more negatively charged particles, or the electrons. So that means that's an atom that took on or gained electrons. And so again, you get a negative charge. So here we can see in these 2 pictures, we have 5 protons to 3 electrons, more positives than negatives. Therefore, it's a cation. Here we have more electrons than we do positives or protons. Therefore, this would be a net charge that would be negative. So protons, like we said, are responsible for identifying the role or the identity of the element. Electrons determine charge. So when it comes to the structure and the forces that keep the atom together, electrons are in that electron cloud, mostly empty space. So it's very easy for atoms, and it's even broken down so much that certain elements have an easier time losing electrons while other atoms have an easier time gaining electrons. And we'll get into that more as we go on. But what I'm getting at is electrons are much easier to be transferred, and again, in a gain or a loss. And that gives us a change in the charge of the atom. The proton, because of the nuclear forces that hold the nucleus together, protons are not easily gained or lost. In chemical reactions, that is when electrons can be transferred and shuffled and things like that. And so again, that's easily done. When you have a chemical reaction take place, protons have nothing to do with that. And so the only way you can gain or lose protons in the nucleus is through a nuclear reaction. And so most of the everyday things we come across that are going through changes are chemical changes, not nuclear. And so when it comes to ions and formation and charge, it has nothing to do with gain or loss of protons, only the gain and loss of electrons. So again, if it has a negative charge, it had to gain electrons. If it has a positive charge, it had to lose. And so again, a lot of times students mix that around. And again, if you think about charge and the net charge, what particles give that to the atom to become that ion, that kind of helps keep those two straight. So here's an example with calcium. And so these are called Bohr models, and we're going to use these throughout the year. And so what we really care about is calcium became a calcium ion. And specifically, it has a +2 charge. So that's a cation. So if we look at the Bohr model, this is the Bohr model for calcium. It should have 20 protons, 20 electrons. And so we have this outer ring of electrons here that we highlighted in green. So this is our before calcium. This is the neutral atom. And so what happens is it likes to get rid of those 2 electrons. And like I said, that's not our battle for today. There's a reason why it wants to do that. But again, we'll get into that into our next unit. But what happened in losing those 2 electrons is it now has 2 less electrons than it does protons. That's where we get the net charge of 2. So again, more positives gives you a net charge that will be positive. Again, looking at the other option on anion formation is we have a example with fluorine. And so in the nucleus, we would have 9 protons because of its atomic number. And when you start with neutral fluorine, you should have 9 electrons. If you take on the gain of electrons, which is this one here, we now have 10 electrons versus 9 protons. You have 1 more negative than you do positive. That's where we get the net charge of a -1. And then we have fluorine with a -1 charge. Let me mention both on this slide and this side here is anytime we talk about an ion and the net charge, we write it as an exponent, or essentially what we call a superscript. We write it in the upper right corner. And so sometimes some people will write it -1. Other instances, you'll see it as a 1-, just depending on the publisher and who's writing it. Either way is fine. So let's take a look at some examples. And so this first one, we have the left-hand side comparing an atom and an ion of oxygen. And so to start out, we're not even going to fill in the symbol yet. Let's fill out protons, neutrons, electrons. So this is trying to represent that this dense center is the nucleus, and this is the nucleus being enlarged. And then these negative dashes around represent the electrons. So if you count up, the protons are the black dots in the center. If you count that up, there are 8 of them. Neutrons are in the nucleus as well, so those in the center, there's 8. And then if you count up the negative dashes in the electron cloud, there's 8 electrons. So when it comes to writing the symbol, we're going to do nuclear notation. So again, that's our symbol O for oxygen. In the upper left corner will be your mass number as our superscript, so protons plus neutrons is 16. Our subscript is our atomic number, which is protons, and that is 8. So if we look at this next drawing, we can see that protons and neutrons did not change. However, if you go through and count our electrons up, we now have 10 electrons. So when we go to write the symbol for an ion of oxygen, we have O. Mass number did not change because protons and neutrons remain the same. We're still talking about oxygen, therefore our atomic number is the same. However, we need to represent that it's an ion, and so that's where we show the charge as a superscript. If you look, we have 2 more electrons than we do protons. Therefore, this is an anion, and the net charge is going to be a -2 because it has 2 more electrons than it does protons. So again, we don't put anything here because it's just assumed it's neutral. But as soon as you start talking about an ion, you have to include the charge and by what extent. So that tells me that there's 2 more electrons than there are compared to the protons. So this is magnesium, and I know this diagram is a little bit difficult to see. If you do the counting of it, in both instances, because they are both magnesium, there are 12 protons in the nucleus. And in each instance, there is 11 neutrons in the nucleus. So when you go to count the negative dashes representing the electrons in the electron cloud, we have 12 here, and in this case here we have 10. When we go to write our symbol, so magnesium symbol is Mg, uppercase M, lowercase g. In the superscript here, it's mass number, so we add that up, protons and neutrons, we get 23. Our subscript is our atomic number, or protons, which is 12. So for the ion of magnesium, we still have Mg. Protons and neutrons were the same in both instances, so mass number is still 23. Protons are the same because we're still talking about magnesium. Now in this instance, we have more protons than we do electrons. Therefore, the net charge is going to be positive. And because there are 2 more protons than there are electrons, we are going to have a +2 charge. So this is an instance of we are looking at a cation, as where oxygen is an anion. So in this next table, I give you the symbol and charge if applied, and we're going to just count protons, electrons. We're going to say what the charge is and then what kind of ion it is, or if it's neutral. So you will need your periodic table if you don't have that out already. So if you take a look, Na is sodium. Its atomic number is 11. Therefore, it must have 11 protons. Okay, let's talk about electrons. So this net charge is a +1, which makes this a cation. In order to become a cation, you have to have more positives than you do negatives. You have to have 1 more proton than electrons. Therefore, this is going to have 10 electrons to give it a positive charge. So in our next example, we have F, or fluorine. Using our periodic table, its atomic number is 9, therefore it has 9 protons. The charge is a -1. Because it's a minus, this is an anion. An anion has a negative charge because it has more electrons than it does protons. So this instance is going to have 10 electrons. Notice here we have no charge up here. This is the instance that the charge is 0 or that it's neutral. This is like what we've done all along, protons and electrons being equal. So you have to find Ar, or argon, on your periodic table. Its atomic number is 18, therefore 18 protons, 18 electrons. Here we have Be2, or +2. Be is beryllium. Its atomic number is 4, therefore 4 protons. I can see its charge is a +2, and it's a cation then because of that positive charge. Again, to have a net charge that's positive, you must have more protons than electrons. So you need to have 2 more protons. So to do that, you can only have 2 electrons. Lastly, we have nitrogen. Its net charge is -3. It's an anion. Using our periodic table, its atomic number is 7. So in order to take on that role of having a negative charge, it must have more electrons than protons, and then it must have 3. So therefore, this one also has 10 electrons in order to get that net charge of a -3. So the last thing is kind of combining together things that we've done and adding the spin of talking about electrons and charge. So in this example, I tell you that the atomic number is 6, mass number is 12, and that this is a neutral instance. So for the neutral, we know the charge right away is going to be 0. Therefore, like we've done all along, if the atomic number is 6, protons and electrons are 6. And then mass number, subtracting those like we've done all along, we have 6 neutrons. Atomic number 6 tells us that this is carbon. Nuclear symbol, we have our symbol C, mass number 12, atomic number 6. In example 2, we have oxygen. Well, I know right away my symbol's O. Using my periodic table, I find that the atomic number is 8, therefore protons is 8. I can go ahead and find my mass number now, protons plus neutrons, to give me 16. So I can go ahead and fill that and atomic number into my symbol. Now let's look at charge. So I have 8 protons here, 6 electrons. More protons than electrons, so this means that this is going to be a plus charge. And specifically here, it's going to be a +2 because we have 2 more protons than electrons. And so is this an anion, cation, or neutral? This is going to be a cation. I need to make sure I add that in to my nuclear symbol because it is a charged ion. In example 3, I tell you the mass is 24, protons is 12. I can subtract those out and get neutrons. I have 10 electrons. And so let's start talking about charge. I have 2 more protons than electrons, 2 more positives than negatives. Therefore, it's a +2 charge, which also makes this a cation. Because I have 12 protons, I have an atomic number of 12. Using my periodic table, atomic number 12 is magnesium. Its symbol is Mg. My superscript is 24, subscript is 12, net charge is +2. In this next one, I have atomic number 24, so I know my protons is 24. Mass number is 52, so if I subtract those two out, I get a neutrons is 28. I'm told that's a +2 charge, so I know that I'm working with a cation. And so the next thing is electrons. I have to have 2 more protons than electrons, therefore 22 electrons will be found here. Atomic number is going to identify it. This is chromium. So symbol is Cr. 52, 24, +2. I would maybe take a minute to pause the video and fill out the remaining 3 examples and see how you compare to my answers. So continuing on with number 5, I have atomic number 17, so I have 17 protons. I know 17 protons, 18 neutrons gives me a mass of 35. The net charge here is a negative, so I know that it's an anion. Moving on from there, because it's a negative charge, I have to have 1 more electron than proton, so add on to that. We have 18 electrons then. Atomic number 17 identifies it as chlorine. Chlorine symbol is C lowercase l. We have 35, 17, -1 for the superscript for the charge. The last 2, you were given the symbol and you're breaking that all down. So I know the superscript here is going to give me atomic number 56 and number 7 is going to be 79. Oh, I put those both in the wrong spot. Let me backtrack. But either way, as I'm erasing these, those really should have went in the mass number spot. I was not watching where I was writing. And then the lowercase number, our subscript, is our atomic number. So let's try this again. So we have 26, 35, 56, and 79. This is also Fe is the element iron, and Br is bromine. Number of protons is going to be 26, 35 from our atomic number. Subtracting mass and atomic number, you should have got 30 neutrons here, 44 for number 7. Okay, so the charges are given here. So I had a net charge of +3 here, -1 here. Positive charge is cation, negative charge anion. To get that positive charge, you have to have more protons than electrons, specifically 3 more protons. So this is 23 electrons. And then here we have a -1. We have to have more electrons than we do protons. So we have 36 electrons, and that fills in our table. So again, the whole new piece of information for today is to figure out net charge and what that means for subatomic particles. Please let me know if you have any questions.